this is not a technical talk. I'll just be ranting on about this fuzzy thing called thinking. And to be less useful, I'll just talk about how I think. Yeah, I warned you. So just let's move on to the problem. Unlike probably most of you, I'm not a full-time Haskell developer, and I have to cope with this fact. And I try to do that by using Haskell at least as my thinking tool, as if not the tool for building the solutions. So let's just move on. What is a thinking tool? That's, again, it's a fuzzy thing. It's hard to describe. I'll just try to explain how I approach this. And I put the techniques into quotes because they're not actual techniques. I'm just going to tell you some short stories, hopefully success stories. At least I see them as such. Let's just dive in and try the first approach. It's just to cheat. And by cheating, I mean using Haskell as a tool, not a thinking tool. Let me elaborate on that. In some cases, it's easier to build a prototype, iterate on it, port it, and throw the prototype away than just to target the platform you have to build for directly. In my case, this was back in college. I took a class on big data / machine learning from Stanford, and we had to turn in assignments written in Java targeting Hadoop. And the type of assignments was such that we had to do quite a lot of iteration and tinkering to get the right results out. And of course, I built my own toy Hadoop example. Here it is. It fits on a slide. It takes about 10 minutes to come up with this code. And it's really useful because the classical hello world of MapReduce becomes this bit of probably readable code. I won't dive into details, but you probably agree that this is much easier to iterate on than a huge Java classes. At least for me, I have trouble thinking in Java and writing out the programs, and I make stupid mistakes. Whereas using this approach, I just started off writing a idiomatic-ish solution in Haskell first, trying it out, iterating, getting something that works, and then refactoring until I could fit it into this model. And I could do this really quickly using GHCI and just getting type errors if I messed something up. And when I was done, I ran it again, and it still worked. So at the end, I just ported that to Java, and it still worked like magic. And I would reckon that this approach, in total, even using coming up with the toy Hadoop, took me less time in total than it would take me if I just iterated on Java. Because of the long compile times and the less guarantees that I got, I would have to write more tests up front and so on and so on. And as a bonus, if I took the extra time to refactor the toy Hadoop example and use more efficient approach and actually beat the Hadoop running on one machine by a factor close to 100. So yeah, it was a nice exercise. Okay, but that's just cheating. Let's move on. I don't have a name for this approach, so I just put this well-known quote in here. And because we're at a Haskell event, I updated it slightly. So if you build something complicated enough, you will encounter concepts that are missing that you know from other worlds, and you will miss them, and you will implement them in an ad hoc, informally specified, but written slow implementation. So what's the point of this approach? It's the moment you have when designing a feature that you say, oh man, this would be so trivial if I just had X, where X is a feature you know and love, like algebraic data types or lenses or anything really. And you just implement the minimum viable X. And this is how you end up with the contrived program that implements everything. But I will argue that sometimes this may not be a bad idea, because some solutions are good and deserve to be implemented even if in an ad hoc way, which is bug-ridden, slow, and so on and so on. And my experience with this was actually building some SQL based on an abstract syntax tree that came from parsing some user input. And I just got this into maintenance, and I had to implement some more features. And I realized I will need to deal with multiple values instead of just one that specifies how to build the predicates, and I will have to join them together using ands or ors and exists and all this stuff around it. And of course, applicatives and effects just popped into my mind, but then I realized that what I actually need are traversals, or traversal from the lens library. And when writing it down on a whiteboard, I realized that I can actually implement a small subset of traversals that's monomorphic and doesn't do anything fancy, but it solves my problem. And I implemented that in Python, and the result was, well, not really idiomatic Python code, because it was full of lambdas and higher order functions, but it is beautiful in its own way, because it really does separate the concerns, and it does one thing at a time. And actually my coworkers loved it, and after doing this a couple of times, they actually started learning Haskell on their own. So I call that a success story. Yeah, this is probably not really helpful of a slide, but sometimes all you need is just to take an inspiration from a concept from some other language or some other library. And you can try to force this inspiration by asking yourself a question. How would I approach this in a different setting? And if you try to think outside of the box you're in, if you imagine you're in a completely different setting, you might get different design ideas. And some of these ideas might be complete rubbish, and you will throw them away. And this is usually what happens. But some of the time you get lucky, and you get to tell a success story. And my story in this case has to deal with object graphs. I'm working on a project that internally has an object graph that it exposes to the users, and it lets them manipulate that graph. They can add connections and remove connections between the objects. Again, this is something that I got into maintenance, and I had to add some more features to it. And the business people decided we want some kind of partial transitivity thing. They were really not sure what. So we whiteboarded on that for a while, and we came up with some simple rules that just talk locally about finding triangles and filling in the third side, where the point in the triangle fits some predicates. And that means that when a user does two sides of the triangle, we automatically fill in the third and fill up the graph that way. And it works locally, and it's nice and fine and everything. So the obvious approach to do that would just be to do some if statements and ad hoc implement the rules. But instead, I went the extra mile and over-engineered the thing by writing a local graph modification engine and DSL and everything. And I ended up with a really nice declarative DSL in Python again that lets you specify the predicates and the rules and the special cases and everything in a way that you can show to a business person, and they can say, yes, that's okay, no, that's not fine, because they can read it. You don't need to translate for them, and you get a much faster feedback that way. And it turned out that the code, the interpreter for this data structure, was actually not a lot longer than it would be to implement just one of those rules. So that was an instant win, basically. But the decision to over-engineer in the first place came when, of course, changes on the specification were introduced. We had to change the structure of the graph, which was a really easy change in the interpreter. And then we had to change the rules, which was really easy because the rules were isolated and really readable. And then we changed another thing because we found that in certain cases you end up with a full graph because the rules cascaded and everything just filled up. So we had to design some limitations on the rules. And again, we did this on a whiteboard, talked about it for a while, and we found some restrictions on the predicates you can impose. And the nice thing about having the rules as a data structure is that you can actually implement the check as a test or do it as a startup of the application. And we did that and actually future-proofed the rules engine to never explode again in this way. So, of course, the inspiration for this approach was the everything is a value in a functional programming setting, and thinking about the rules as a free monad or something, even though the implementation does not look anything like free monads. But thinking about it, how would I approach this if I had a purely functional language where everything is a value, including the rules, gave me nice inspiration on how to approach the problem in a way that yielded nice engineering results. And that concludes my short stories of success. And of course, I'm open to any questions, if you have any, that is, because there was not a lot of information to learn from this. Yes?
I think you should mention which company you are doing these experiments for.
Oh, of course. I'm working at Reciprocity, who is doing government compliance software for big corporations in Silicon Valley. And we have a big Python code base that's slowly getting more functional in every meaning of the word. Yes? Actually, I have some running as just local development tools, nothing in production yet. And I'm slowly building up interest among coworkers, so we're moving in that direction slowly.